the area as well, right? Or this is the rotation. So all these things we can do, right? Okay, but let us do this question. Okay, so this is the question, and we want to find out the magnetic flux in Weber is given by this. The magnetic induced EMF is required at the fourth second. So induced EMF at the fourth second. So we want to find out induced EMF, right? So induced EMF at the fourth second, right? So that is what we want to find out. And we know that what is the induced EMF? The induced EMF is minus d phi by dt, right? So we can calculate this induced EMF, and what would be that? This would be minus of d by dt of this whole thing. So this is the induced EMF, right? And what would be this? This would be minus of, we can ignore the minus sign, right? Because this is only talking about the Lenz law. This is only talking about the direction of the induced. So we can ignore this. This would be 10t plus 3, right? So this is how the EMF is changing. Now, if we look at the question carefully, right? If we look at the question carefully, so they are saying that what is the induced EMF in the fourth second, not in 4 seconds, right? Not in 4 seconds, but in the fourth second. So what we can do is that we can calculate, let's say we can calculate up to 4 seconds, right? And then we can calculate up to 3 seconds, and then we can just calculate the 4 second minus the 3 second. So this would be the fourth second, right? So let us calculate what is E4. This would be 10 into 4 plus 3, so that is 40 plus 3, that is 43. And what is the EMF after the 3 seconds? So this is 30 plus 3, so that is 33. So EMF at the fourth second, this would be E4 minus E3. So that is 43 minus 33. So that would be 30 10 volts, right? And if you look at the question, so they have given this option as well. So this is just to confuse you, but this is the correct answer, right? So quickly note down this thing, and if you guys have any question, please tell me. This these kind of simple questions you will get, right? These kind of simple question you will get, and you have to just remember the form, right? Quickly note down this thing, and whenever you have noted, please tell me. If you guys have, if you guys have, so what is the issue? So now this is EMF generated using the change in flux as a whole, right? Now there are other methods as well. So one is that we can change. Okay, so 800 has kept magnetic field in plane uniform. Yeah. So this is the same question. Fifth one is the same question, and the radius of the loop is made to shrink. Yeah, this one. So we can do the sixth question, and then so this is the question that we can. So this is also the same question as conducting circular loop placed in a uniform magnetic field perpendicular to the magnetic field. The radius of the loop starts shrinking at 2 millimeter per second. The induced EMF in the loop when the radius is 2 centimeter, right? So that is the thing that we have to calculate, and this is also the same question, right? Both are the same question. So let's do this question. And in this question, what is changing? So the area is changing, right? You can have magnetic field changing, you can have the other thing changing. So let me just talk about that. So in this question, right, in this question, dB by dt. So magnetic field is changing, right? The magnetic field changes with time. Magnetic field is changing and area remains the same. So you can have different scenarios. Magnetic field changing, area changing, and angle changing. In the second question, angle is changing, right? So all these are different kinds of question. Okay, but let us do this one type and then we'll move on to the next topic, which is EMF, right? Okay, so a conducting area is placed in a uniform magnetic field. So magnetic field is fixed. This is fixed, which is 0.025 Tesla. This is fixed. With its plane perpendicular to the loop. So the magnetic field is perpendicular to this plane. This is the plane and this is perpendicular. So the direction of this area, this is also in the same direction, right? So the angle is 0 degree. So cos theta is 1. So cos 0 is 1. And now we have area. This is changing, right? What is area? Area is pi r square. This is the area, right? And how the area is changing? So dA by dt. This is pi 2r and dr by dt. So this is how the area is changing. Now the rate of shrinking of radius is given. That is 1 millimeter per second. So this is dr by dt. Rate of shrinking of radius. That is given. Right. Now we want to find out what is the induced EMF when the radius is 2 centimeters. So what is the induced EMF? Induced EMF is minus d phi by dt. We can ignore the minus sign. D and phi is BA cos theta. But cos 0 is 1, so this is only BA. Now B is constant, so this is taken outside. And we have dA by dt. We have already calculated what is this dA by dt. So this is 2 pi r and dr by dt. How much is dr by dt? That is 1 millimeter per second. So magnetic field is 0.025 Tesla. This is 2 into 3.14 and r is 2 centimeter, which is 2 into 10 to the power minus 2 meters, and this is millimeters. So which is how much? 1 into 10 to the power minus 3 meters. So now everything is in SI units, and the answer is in pi. So we can keep the pi. So we have to write this as pi. So this is 2 and 2, 4, and 4 into 25 is 100. So this would be 0.1, and then pi, and then this is 10 to the power minus 5. So we can take this 1 0 in this one, and this is pi into 10 to the power minus 6 volt. And what is 10 to the power minus 6, guys? What is 10 to the power minus 6? 10 to the power minus 6 is micro. And how it is represented? It is represented as m. 10 to the power minus 3 is milli. How it is represented? It is represented as m. So we can write this as pi micro. This is the answer. Right. So this one is the correct answer. Is it clear, guys? If it is clear, then quickly note it down. Quickly note it down, and then we'll talk about the next topic, which is the emotional EF. And now you guys already understand that we can also change the magnetic field. In this one, we fixed the magnetic field. We can also change magnetic field and keep the area fixed. So we can have different questions. Whenever you guys have noted, give me one. Yeah, so whenever you guys have noted, yes, whenever you guys have noted, please.
Noted, sir.
Okay, so you guys can practice rest of the questions as well. And you can just find out that in this one, angle is changing, right? And in this one, magnetic field is changing. And in this one, the whole magnetic flux is changing. In this one, area is changing. And yeah, so these are the kind of questions that you have. Okay, and this one is related with the EAB, right? So this one you can. Okay, so now let us talk about the emotional EAB, right? So let us talk about emotional. So in the emotional EMF, what do we have? We have the magnetic field that is fixed. Now you guys already know that how we can create EMF. We can create EMF by changing the flux. Right, this is how we can change the EMF. And we know that this phi is dependent upon VA and cos theta. So this is how we can change it. That's right. And let's say that we have a magnetic field which is going inside. So this is the magnetic field, and we are talking about motional right. And what we are doing is that we have this aperture, right? This is the aperture, and this is some wire which is attached to it. So this wire is attached, and this wire can move, right? This wire can. So now, let's say that if we have some area, right? If we have some area which is this, now we move this thing to this point, right? So we move this thing, and this comes here. This wire comes here. Now the area has increased and it has become this one. So what is changing? Area is changing, right? And you guys already know that how we can create the EMF. So the magnetic field is fixed, that is constant, but area is changing. And if we can change the area, let's say that this is the distance x, and this is changing. So now this will become x. So this x is changing, but this length, let's say L, this is not changing, right? This L is not changing. Only this side is changing. So area would be how much? Area would be x into L, and change in area would be how much? dA by dt. That would be d by dt of Lx. L is constant, so we can take it outside, and this dx by dt. This dx by dt is only velocity, so this would be Lv, right? Now we know that what is the EMF generated. So this is minus d phi by dt, and it's area vector and magnetic field. They are both in same direction, so theta is 0 degree. Theta is 0 degrees, so this thing is how much? Minus d by dt of VA. So B is fixed, and we can take it outside, and this is dA by dt. dA by dt we have just solved. This is LV. So EMF is minus BL, right? So this is what we call motional EMF. This is what we call motional EMF, and you can also have, let's say, you can see that this motional EMF is due to the velocity of this thing. So this is moving with the velocity, right? So this is the EMF, and then we can also calculate what is the resistance or what is the current. So current is E by R. So this would be minus BLE by R, right? And we can also calculate the power in this thing. So power is I square R. So this would be V square L square V square by R square into R. So this will cancel, and you will have V square L square V square by R. So this is the power. And these are the crucial thing of the motional EM, right? And then you can also have, and then you can also have the, let's say you have the same magnetic field, but the coil is rotating. So this is the length of this thing, and this is rotating, right? This is rotating. So what would be the EMF of this thing? So what would be we know that this E is d phi by dt, right? And we know that this is small de. So this is small de would be simply b, and whatever this length is, let's say x and d, right? Or we can write this as, so this is bv and dx, right? Because we know that EMF is BLV, and this distance is x. This small distance is dx, and it is rotating with v velocity. And we know that this is the circular motion, so this linear velocity would be omega x. And we can write this as omega x dx. So then we can integrate this thing, and we will get, so this would be half b omega and x squared. And we know that what is the limit of this thing? So this is from 0 to r. So this thing would be simply half d omega r squared. So this is the EMF of a rotating one, right? This is the EMF, motional EMF of this rotating one. And yeah, we'll talk about AC generator at some point later. And yeah, but now we'll talk about the inductance. So just note down this part, and then we'll talk about the inductance. Quickly note down this. Whenever you guys have noted, please yeah, whenever you guys have noted, please yeah, whenever you have noted, please tell. Noted. Yes, did you note it down, Adil? I guess your microphone is not working. Yes, Yes, what is happening to your internet, guys? What is happening? Yes, hello, Alia, can you hear me? What is happening to your internet, guys? I guess your internet is not. Yes, you are back. You are back in Terminator's voice, right? So Nabil in Terminator's voice, as Arnold Schwarzenegger says, you are back. Okay, so what we were doing, we were just talking about that how we can change or how the emotional EMF is generated, right? Oh, a call came in. That's how I did. Okay, yeah. Okay, so yeah, these are the example of emotional EMF, right? And now let us talk about the inductance, right? What is inductance? But before we talk about the inductance, let us talk about the law of inductance, right? So it says that in the flux generated in some coil that is directly proportional to the current that is flowing. And then if we remove the proportionality constant, so we will get a constant, and that constant is called the inductance, right? And this can be of two types. So this can be mutual whenever you have two coils involved. So this would be mutual inductance, and you can have self inductance as well. So you can have mutual inductance and you can have self inductance, right? So let us talk about mutual inductance. What is that? So let's take the example of solenoid. So solenoid, and from this thing we will understand what is mutual inductance. So let's say we have two coils. Oh, what happened? And then we have some inner coil, right? And let's say this one has N2 number of turns. This one has N1 number of turns. In this one, the current is passing I2. In this one, the current is passing I. So let's say if current I2 is passing, so this will create some flux in the secondary coil. And this secondary coil flux, that phi 2, this would be directly proportional to this, let's say this is in the secondary coil, so let's write it as phi 1. And this would be directly proportional to this I2 current, right? And now because we have n number of turns, so this would be N1 5, right? So this N1 phi 1, this would be equal to, if we remove this proportionality, so this is due to 2 in 1, and this is I2. So this mutual inductance, this would be equal to N1 phi 1 divided by I2. Similarly, if we talk about the current in I2, I1, and then this will create some flux in this thing, right? So this N2 phi 2, this would be directly proportional to I1. If we remove this proportionality, so we'll get because this is 2 in 1 and this is I1. So M21, this would be equal to N2 phi 2 divided by, and this both these things are equal. So we can write this thing as N1 phi 1 by I2. This is equal to N2 phi 2 by I1 because we have M21. This is equal to M1. For both, I have written M21. This is this is 1, right? So mutual inductance in 2 due to current I1. Mutual inductance in 1 due to this 2 part, right? So that is how. So this should be, yeah, this should be 2 1, right? So this should be 2 1, and this should, so mutual inductance in 1 due to the current 2, mutual inductance in 2 due to current I. So that is how we identify this thing. So this is what we call mutual inductance, right? Similarly, we can have the self-inductance. And what is self-inductance? So this is the coil, and let's say current I is passing. So due to this current I itself, there will be some flux, and there would be some inductance. And what would be that? So this, let's say the number of turns are n pi, and then this would be directly proportional to I. If we remove the proportionalities, this would be L, right? And now we can calculate. So we can calculate what is this flux generated, right? This flux generated is PA cos theta. And we know that theta is 0 degrees, so that would be only NBA, and this is equal to L. And now we know that what is uh, what is the magnetic field in a solenoid. The magnetic field in a solenoid is mu naught, and this is Ni, and this is A, right? So we also know that what is this N? So this N is N pi, or we can write this as because we know that this N, small n, is number density, and we can write number density as N by L. So we can write the total number of turns as N into L. We can put this value in here. So this is N into L, mu naught, N I A, and this is L I. I and I will cancel, and you will get the self-inductance as mu naught N square and L and A. So this would be your self-inductance. And if this is placed in a medium, so in a medium, if this whole system is placed in a medium, so this L would be simply, this mu naught would be replaced with mu, and this is N square L. And we know that what is this area of cross section? So you can replace A by pi r square. So you can also write this thing. So this is self-inductance, right? This is self-inductance, and due to the self-inductance, you can calculate what is the EMF generated. So EMF generated in an inductor, EMF generated would be how much? We know that this is d phi by dt, and we know that this phi is n phi, right? N phi by how much would be this? So we can write phi as because there are n number of turns, so this is n phi, and now we can write this thing as Li. So this is n, right? Or we can write this thing as because n phi is Li, so we can write this thing as d Li by d. So L is a constant. We can place it outside. So this is di by dt. So this is the EMF generated. This is the EMF generated in an inductor. You know that what is the EMF generated in a resistor? This is simply IR. Do you know that what is the EMF generated in a capacitor? So that is how much? Q is C V. So V is Q by C, right? So this is Q by C. So for capacitor, this is Q by C. For this resistor, this is IR. For inductor, that is LDI by dt, right? So these are the three ways we can get EMF. And we also know that we can also calculate what is the energy of the inductor. So energy of the inductor, we know that energy of the inductor, I will directly write. So no need to derive that thing. And this energy is simply half Li square. So no need to derive that, right? Because we know that work done is simply by R, right? So this is E by, we can write that what is power? Power is VI, and we can write that thing. So power is VI. So this is how much? This is L di by dt into I, and then you solve this thing, and then this power is dw by dt. Dt will cancel. You solve this integration, and then you get half Li. So this is how you get the energy of the. So this is all about EMI chapter, right? This is all about EMI chapter. You guys note down from here, and then yeah, we'll see if we can how much time. We have half an hour, so we will start easy, right? We'll start easy. What you guys note down this part, and whenever you guys require me to scroll down this screen, please just note down all these portions, right? So quickly note down this thing, and then we will talk about chapter 8. Whenever you guys want me to scroll down, please. Yeah, whenever you guys want me to scroll down, please. Yes, noted up to this point, guys. If you guys have noted up to this point, then please note down this portion. Yeah, please note down all this part, and whenever you guys have noted, please just note down all these formulas somewhere, right? So just note down all these things in some notebook, and you just have to remember all these. Okay, so yeah, whenever you have noted these steps, give me one. Whenever you guys have noted these steps. Okay, noted. Good. So now let us start. Let's start. Can we do some questions, right? Otherwise, we won't be able. Okay, so directly proportional to. Yeah. So all these questions are the self-inductance, right? So you will have some direct questions. A long solenoid has this much turns. When a current ampere flows, read the magnetic flux liquid is solenoid is this. The self-inductance of this solenoid, right? So yeah, you can just find out what is the self-inductance. So you have to use just direct the formula, right? So yeah, these would be some simple questions. So we'll skip this part and let us start the next chapter, which is the next chapter is this, right? So first, let us understand that how we generate AC, right? How do we generate the alternating current? So we already know that how we can create the EMF. So we already know that how we can create and this is by changing the flux, magnetic flux. So this is how we can create. Now we also know that this flux is dependent upon VA cos theta. So we can write this thing as VA cos theta. And by changing any of these three things, we can change the flux and correspondingly we can get what happens in AC generator, right? What happens in AC generator? So in AC generator, you have this constant magnetic field, and then you have this aperture, and this is connected with some right, and then this is connected with inverter, and these are rotating. So this area is fixed. Only this part is rotating, right? So let's say this is the axis of rotation. So this is rotating, right? This you can rotate, but this magnetic field and this area is fixed. So you have B fixed, you have area fixed, and how the angle is changing. Theta is omega t because angular distance is changing, right? Angular velocity is constant. This is theta by t. So theta is omega t, right? Theta is omega t, where omega is angular velocity. Right. Now we know that we can write EMF as minus d by dt VA cos omega t. In place of theta, we put omega t. P is constant, we can take P and A outside, minus d by dt of cos omega t. So differentiation of cos omega t would be how much? That would be minus of sin omega t. And what else there? What else would be there? What would be differentiation of cos omega t? What is that? One moment. Yeah. So what is the differentiation of this? So this is first we have to apply the chain, right? Chain we have to apply. So first we'll do the trigonometric function. This would be minus sine omega t. And inside this trigonometric function, we have this algebraic function. So we'll take the differentiation of omega t. That would be simply omega. So this would be minus omega sine omega t. So this, there would be an extra omega in here. So this would be PA omega and sine omega t. This is the right. And we can put this PA omega as a constant. So this is E naught sine omega t. Right. So we can write it as E equals to E naught sine omega t. This is the how is it varying? So this is how the EMF is varying. Oh, and this is varying, right? And you have a maximum and you have a minimum, minimum and maximum. So this is minus E naught and this is right. And this is 0. This is pi by 2. This is pi. This is 3 pi by 2. This is 2 pi and so on. This is how the EMF is varying. And this E naught, this E naught is called the peak voltage. Right. So this E naught is called peak voltage because this is the maximum voltage that we have. So you guys, if you guys have no doubt, please note down these things and then we will talk about the other. Please note down this part. Right. And then we'll talk about different circuits. And in the next class, yeah, so I will try to start on this. Right. Yes, noted, guys. Guys have noted still. Okay, good. So now let us talk about that. Now, all the previously, right? Previously, whatever the supply that we were talking about. So in the EMI chapter, right? Whatever up to first to six chapters, whatever EMF we were taking, that was direct, right? So this was DC current. In DC current, your I was fixed, your voltage was fixed. But in AC current, this is how it is represented, right? In AC current, as the sign says, this is varying, right? So your this is called AC current, and in AC current, you will have I, which is varying, and your V is also varying, right? And there is a very important thing to note down here that we have understood in the third chapter that how we can add resistances simply, and how we can add voltage simply, how we can add current simply. But in this case, we cannot add current in this way. We cannot add voltage in this way, right? So we will have to use the vectors item, right? Because why we cannot add them? Because they have different phases, right? They are not like terms. So they have different phases, so we cannot add them in algebraic way. In the DC supply, you saw that we can just add these things in this manner, but we cannot do in this case. And before we talk about how we can simplify the scenario, so we can convert this AC into some approximate DC supply, and that we do by changing this AC current or this thing into RMS values. Root means square values, right? So we convert this thing, and this would be the overall voltage that would be getting. So whenever we are talking about AC chapter, so the current and the voltage that we are talking about, that is only the RMS current and the RMS voltage. So, but before we talk about RMS current and RMS voltage, let us find out what is RMS voltage, right? So we know that we have this supply. This is the voltage supply that we have, and there are four things in here. One is the peak voltage. So peak voltage is E naught. Then we have average voltage in full time. In full time. And what is full time? So we talk about from here to here. So you see that in this full time period, this would be zero because this part is positive, this part is right. So in full time, this is called E average, and this is zero. In half time, right? In half time, what is that? So average voltage in half time. So this is E average in half time, and that is 2 E naught by pi. So this is the average voltage in half cycle, so half time or half cycle. And all these are known results, so I will not derive all these things, right? And then we have RMS value. So what is this RMS value? RMS value is root, mean, and square value. So first, what we will do is that we will square. So we will square, and then we will take mean. So this is how we approach, right? So first we will square it, and then we will take the mean. So that's it. That is how we denote mean, and then we'll take the root of this thing. So this is what we call mean square. And if you solve this thing, so this is E, which is E naught sine omega t whole square. And if you take the average of this thing, E naught is a constant. So this thing is taken outside, right? And then this is outside. So let's say this is E square and sine square omega t. And then you are taking the average of this thing. So E naught square is a constant. It comes out of this average and then comes out of the root. So this becomes E naught. And then you have to take the average of sine square omega t, and then you have to take the so average of sine square omega t. You just remember this thing. So average of sine omega t is half, and if you take the average of this thing, so this would be E naught by root. So this is the RMS value. So this is the overall supply that you get from an RMS circuit. So the supply that you get is ERMS, which is peak by, and whatever question that you are getting. So in the AC question, they will always give you this RMS value. So just note down this part, and then we'll talk about different circuits. Just note down all these parts are important. So just note down this part, and then we'll talk about the next. Quickly note down this part. Yeah, whenever you guys have noted, please tell. Noted. Good. So now let us understand the other topic. Let us understand the other topic, which is the combination of circuits, right? So circuits in AC supply. right? So first circuit is, let's say we have a resistive circuit. So we have a resistive circuit, and in the resistive circuit, this is the supply that you are getting, and this is R. So the current would be how much? We know that this is IR. So in resistive circuit, if it is connected to the AC supply, this AC supply you are getting from the AC generator, right? So current would be simply E by R, and this is E naught sine omega t divided by R. So E naught by R you can write it as I naught, and then this is sine omega t. So you see that in resistive circuit, the current is with the same phase as voltage. So E is E naught sine omega t, and I is same. So if you plot these two things together, so this is your let's say voltage, and then this would be your current, right? So this would be your current. So wherever the maxima is happening, the maxima is happening for the same case, right? So minima and maxima are in the same line, right? So this is varying similarly. So they are in same phase. But for the case of, let's say, inductive circuit. So let's talk about inductive circuit. So what do we have in the inductive circuit? So we know that this is LdI by dt, right? So so I would be how much? I would be, this is E and dt and divided by L. This is your I, but yeah. So this is your I, and we know that what is this? We know that this E is how much? This E is E naught sine omega t and divided by L and d. So E naught by L, we can take it outside, and this is integration of sine omega t. And integration of sine omega t is minus of cos omega t. This is minus of cos omega t. And then you have a division of omega. So this becomes E naught by omega L and minus of cos omega t. Right. So you see that this thing is we can write it as sine omega t minus this pi by 2, right? So this is in the fourth quadrant. In fourth quadrant, cos theta is negative, right? So we can write this thing as minus pi by 2, and omega L we can write it as xl. So you have an inductive reactance, and this is what we call XL, and this is omega, right? And then you see that the current is lagging behind. So this is minus pi by 2, right? So we can write I as I naught sine and omega t minus pi by 2. So current is lagging behind the voltage. And how much is the lag? So lag is 90 degrees, right? How much time do we have? So you guys note down these parts, and then yeah, in the next class I will finish this thing, and then we'll talk about the other chapter, which is optics science. Optics. But you guys just note down all these questions, right? I will is the chapter in the next class, and then we'll start the next chapter. Yeah, whenever you guys have noted, so here current is lagging. Whenever you guys have noted, just yeah. Yeah, so we'll stop here, and in the next class we'll try to finish this thing, and then yeah, then we'll start the new chapters. Yeah. Alia, did you note down this part? Okay, so we'll stop right. Yeah. If you have noted, then see you in the next class, right? If you have so Allah Hafiz, Ali. See you in the next class. Yes, Alia, did you note down this part? Yes, Alia, can you hear me? Have you noted it down? Yes, can you hear me, Alia? Did you note down this part? Yes, Alia, are you here?